This is the first video of a playlist about architecture analysis. In this video I introduce the 5 major goals of architecture analysis based on Automotive SPICE and the V model. I like to use the V model because it gives you the big picture, it's easy to remember and understand, and helps you retain most of the content of this video. I'll use the V model of software engineering, but it would be the same for electrical engineering or systems engineering. The concepts are the same. So stay with me and learn about architecture analysis. I believe this video will help you in your project, level up your process skills, and help you prepare for an Automotive SPICE assessment. I'm Giuseppe, I'm a principal assessor and instructor in Automotive SPICE. If you like my videos, subscribe to my channel. Thanks a lot. Now let's start with some definitions based on the V model. In the V model, architecture analysis are performed between requirements and implementation. Requirements describe the problem. They define what must be achieved. Implementation is the solution. For software, this is the code. For hardware, it's a populated PCB. Between problem and solution, we have the design. Architecture is the high-level design. It describes the main functional blocks of the software or of the hardware and their interfaces and interactions. At lower level, we have the detailed design. This describes the individual software functions, also called units, or schematic and PCB layout for the hardware. Now the question is, why do we need an analysis of the architecture? That's very easy. Architecture is the place where the most important decisions are made. These decisions shape the solution. Once the architecture is fixed and the detailed design and implementation begin, changes become difficult, expensive and risky. That's exactly why architecture is so critical. For these reasons, standards like Automotive SPICE, ISO 26262 and ISO 21434 all require a dedicated analysis of the architecture. An architecture analysis is a systematic evaluation of a system, software or hardware architecture to ensure it is suitable, feasible, verifiable, high quality, and free of critical risks or vulnerabilities, providing a documented support for design decisions and project planning. In the next minutes, we'll deep dive into these 5 major targets of architectural analysis. The first target of an architectural analysis is to ensure suitability. From the architecture, we look upwards in the V model toward the requirements. The key question is simple. Is this the right architecture to meet the requirements? Suitability means checking whether the architecture can deliver all required functionalities across the entire life cycle of the product, including production, maintenance and decommissioning. If required functions are missing or lifecycle needs are not supported, the architecture is not suitable and therefore not useful, no matter how well it's implemented. That's why suitability must be analyzed early before moving on to detailed design and implementation. If you are an Automotive SPICE expert, you'll recognize that there are commonalities between suitability and consistency. Consistency ensures that requirements are correctly allocated and fully represented in the architecture. Suitability, on the other hand, asks whether this is the right architecture. Can it actually deliver what requirements demand? For example, a safety-critical function might be correctly allocated to a component of the architecture. This is consistency. But if this component cannot meet the required timing, resource targets, or ASIL constraints, the architecture is not suitable. Consistency and suitability overlap, but suitability is stricter because it also covers functional capability, safety, and lifecycle considerations. This is why ISO 26262 explicitly requires it. In short, consistency is necessary but not sufficient for suitability. The second critical target of architectural analysis is the technical feasibility. Simply put, technical feasibility asks the question, can we actually build this? Here we look downstairs in the V model toward implementation. This is about checking whether the architecture can be realized with resources, technologies and constraints available. Technical feasibility covers several key aspects. First of all, availability. Are all required hardware components, sensors, or system elements available on the market? And does the team have access to the technology needed to implement the design? Next is reuse. Can existing software modules, libraries, or hardware components be reused? Reuse helps reduce development time, cost, and risks. Finally, manufacturability. This answers the question, can the system be efficiently produced, and are there design choices that make production easier or less expensive? Performing a feasibility analysis gives confidence that the design is practical, implementable, and ready for the next steps in the V model. Now we move to the right side of the V model, where we meet verifiability. At this stage, the key question is, can this architecture actually be verified? This involves several considerations. First, interface descriptions. Are all interfaces between the software components or between the hardware or system components clearly defined? And can test cases be derived directly from these interface specifications? Second, dynamic behavior. This is about describing the behavior over time. For example, is the ECU startup sequence fully documented and testable, and can we verify how components interact during normal operation, fault conditions, or system tests? In software engineering, the dynamic behavior of the software can be represented by means of state machines, sequence diagrams, etc. Third point is resource usage. This answers the question, are measurements of CPU load, memory usage, or bus utilization feasible, and can we ensure that the system will operate within resource constraints under all conditions? Verifiability ensures that the architecture is testable and measurable. Without it, even a suitable and feasible architecture that cannot be fully verified creates risks for safety, reliability, and compliance. So far we have talked about architectural analysis in terms of suitability, feasibility, and verifiability. But the architectural analysis does not stop here. We also need to analyze the architecture itself. This means checking not only what the architecture does, but how it is described and whether it follows design principles. And this brings us to the next key point of this video, analysis of the architecture against defined description principles and design principles. Remember, one of the main purposes of an architecture is communication. Architecture documentation must allow all affected stakeholders, like for example developers, testers, safety engineers, to clearly understand what each component is responsible for and why the architecture looks the way it does. I call this comprehensibility. From an analysis perspective, we verify whether the documentation provides sufficient architecture descriptions, including component responsibilities, static views, dependency views, dynamic views, always with enough explanation to make them understandable. The architecture has also to justify important design decisions with a clear and explicit rationale. It explains why a specific architecture was chosen and or why alternative solutions were rejected. And finally, the architecture has to make assumptions explicit instead of leaving them implicit or hidden. If you want to learn more about architecture descriptions, refer to the ISO standard 42010. Next, we analyze whether the architecture complies with established design principles and guidelines, like for example solid principles, separation of concerns, dry, and modularity, and other principles that help manage the complexity. This also includes look at long-term qualities like checking if there are parts of the architecture that are difficult to modify or extend. These aspects directly influence quality attributes like maintainability and robustness. Architecture analysis also checks whether resource and performance constraints are addressed at architecture level. This checks, for example, if the software fits with CPU, RAM and ROM resources, and if potential performance bottlenecks are identified and addressed. To close this session, remember this: a good architecture must be understandable, well-structured and future-proof. This is why architecture analysis must always include an analysis of the architecture itself against clear description and design principles. Architecture analysis has also important interfaces with project management and risk management. On one side, architectural decisions can have a direct impact on effort, schedule, and product costs. This is the interface to project management. Decisions that affect these goals must be communicated to the project management team so that they can adjust planning, estimates, and resource accordingly. On the other side, architecture analysis plays a critical role in risk management. Here the focus is on identifying technical risks such as potential performance issues, reliability concerns, or robustness problems. To make an example, under certain conditions, the power consumption of an ECU might exceed the limits. This risk needs to be documented and treated appropriately. From a standard perspective, the ISO 21434 requires performing security weakness checks to identify potential vulnerabilities. These vulnerabilities must be then used in risk assessment to determine new or updated risk treatment decisions. Also, ISO 26262 requires functional safety analyses at the system, hardware and software level, including hazard identification, failure mode analysis, and dependent failure analysis. The results of these analyses feed into the safety risk assessment and definition of safety measures to prevent or mitigate hazards. By detecting risks early in the project, architecture analysis provides a documented basis for decision making, enabling teams to define risk treatment strategies and make informed design choices. I call this property manageability because architecture analysis supports project planning, realistic estimation, and early identification and treatment of technical, safety, and cybersecurity risks. In summary, architecture analysis is performed for 5 critical reasons: ensure suitability, verify feasibility, enable verifiability, assess comprehensibility and maintainability, and support manageability. Architecture analysis is more than a technical check. It's the foundation for safe, robust, and predictable development, supporting both engineering and project management. If you like this video, drop a like and continue watching my playlist on architecture analysis. Thanks for now and arrivederci.